In this video, I'm going to give an introduction to Solidity. Solidity is a programming language that was originally created in 2014, and it was designed to allow development of smart contracts for the Ethereum platform. Now, you could use Solidity to develop smart contracts for other platforms as well, although this lecture will specifically be about the context of Ethereum. So let's start by taking a look at a short but complete Solidity program that could be compiled and turned into a smart contract on Ethereum. So if you have experience programming in languages like JavaScript, Java, C, C++, this code should look fairly familiar to you, and you should be able to read it right away and get some understanding of what's going on. Now, if this code doesn't look familiar at all, you might need to take an introductory programming course before following this video or taking this course. This isn't designed to be an introduction to programming if you have no programming background at all. So like I said, if you've programmed in an imperative language, things like C++, JavaScript, the syntax of Solidity should look fairly familiar. The way things like blocks are defined using brackets, the way if statements or for loops, all of that should be old hat for you. Solidity also has some object-oriented features. Specifically, contracts serve the role of objects in this language. And it's a statically typed language, so the compiler will actually do type checking for you. The basic unit of any Solidity program is a contract. A contract in the programming language serves roughly the same role as a class in a language like C++ or Java. Now this contract is actually legal. It would compile, but of course it doesn't have any methods. It doesn't do anything interesting. This would be sort of a null contract. So the first interesting thing we can do is we can have the contract actually have some storage. So this is a very simple example. This contract stores just a single integer, and we've defined one function so that this contract can be called, and of course every time that function is called, that counter is going to increase. So that's all that this simple contract could do, but that's just to illustrate that any variable that's scoped to the contract specifically will be part of that contract's storage when it's created and deployed on the Ethereum network. And it's important to note here that everything in Solidity is initialized to 0, so that count member variable, which again is part of the contract storage, that's going to be initialized to 0 when a new contract is created, and it can be used right away. There's no such thing in Solidity as an uninitialized value. Of course, a contract can define as many functions as you want, and the functions are what enable interaction with the outside world. The functions are what people can call to get your contract to actually run some code. And notice, of course, like in other languages you may have seen, functions can be defined to be public, which means anybody in the world can call them by creating a transaction on the blockchain, or you can mark your functions as private, which means that they can only be called internally from within the contract itself. Constructors are a special type of function. They're called only when the contract is created initially. And note the syntax here. You actually don't use the keyword function. The keyword is constructor. Older versions of Solidity actually define a function similar to the way it's done in Java or C++. They define a function that has the same name as the contract itself. But the modern standard uses the word constructor to try to make it clear that this is a special function that's only going to be called once when the contract is created. And that's probably a good time to note that Solidity is still a language that's very much in development. A lot of features and syntax are still changing. There's already some old stuff that's deprecated. So if you're watching this video several years after 2018, some of what I'm saying now might be out of date. The complete set of functions that you define for your contract define what's called the contract's ABI, which stands for Application Binary Interface. And that's the interface that others can use to call your contract. So just as an example, this happens to be the ABI for ERC20, which is a very, very common interface for contracts that allow users to create and transfer tokens between each other. But whatever set of functions you choose, that's going to define the interface that people can use to interact with your contract. So let's talk about the data types that are available in Solidity. the basic types should look very familiar. There's Boolean for true false values, a variety of different sized integers which can be signed or unsigned. Notice that the sizes go all the way from 8 bits, the smallest, to 256 bits. The Ethereum virtual machine uses 256-bit words, so it's very natural to define 256-bit signed or unsigned integers. And in fact, if you just declare an int or a uint without specifying the size, the default is a 256-bit size. And every multiple of 8 bits in between is defined. So you can have an int64 or an int72, whatever you want, again, up to 256 bits, which is the largest size. And then there's also a type byte, which is just an 8-bit value and various sized fixed byte arrays. So notice what's not here. There's no floating point numbers, and there's no pointers. So not having pointers maybe is similar to something like Java. Not having floating point numbers is somewhat unusual for a programming language. Although it's turned out most smart contracts don't need to use floating point numbers. There is a proposal to add fixed point numbers to Solidity. But if you really need the functionality of floating point, you'll have to implement that yourself by creating some library code that will do that for you. So moving on to some more Solidity-specific and Ethereum-specific data types. Address is a very common data type in Solidity, and of course this is used to store the address of a contract or an external account. And even though an address is a basic data type, it's really just an alias for a 256-bit value, so you can cache this back and forth if you want to from a 256-bit integer. There are some functions that you can call that look kind of like an object-oriented syntax, even though, again, that address is really just a 256-bit basic type. But you can do a transfer directly to an address. So if you want to send some money to an address, very common, you just call .transfer, and the compiler interprets that to send money to that address. Again, much like in C, C++, Solidity has structs, very commonly used. So if you want to group some related values together, say you have something like records corresponding to a specific voter for your application, you might group a couple of different related fields together, and then you get a nice sort of object-oriented syntax if you want to assign values to those member variables in your struct. And notice with structs, just like everything else in Solidity, they're initialized to 0. So in this line, as soon as you've declared this voter variable, it's usable, and every single member of that struct is going to be given a default value of 0. So an address of all zeros, a Boolean value set to 0 has a value of false, and an integer set to a value of 0 will just be the integer 0. So that's what you're going to get, and it can be used right away. Another useful feature, which you've also probably seen in other programming language, are enums, enumerations. Very common. Suppose you're defining a game. Instead of hard-coding integer values like 1, 2, 3, and 4 for the different suits of cards, say, you can define an enum, and that will automatically give a hard-coded value, and then you can call it quite nicely, as you see here. So for a lot of different applications like games, this is a useful feature to have. Okay, and then slightly more interesting, there are dynamic arrays built into Solidity. You declare them using a syntax like this. Notice that the way this array is being allocated here, it's actually this memory keyword is a note to the compiler that you'd like that value to be stored in memory, which is a little bit different from storage. The main difference is that this will get wiped out every time the function is called again, so this is not persistently stored between calls to the contract. But you can dynamically allocate the runtime will dynamically allocate as much space as you need for this array of integers. And then, of course, you can write to it, and you can even query the length. And like I said, it's dynamic, so it is actually possible to change the length after you've allocated it. Probably the most interesting and quirky Solidity-specific construct is this mapping type. So it works sort of like a hash map in Java or C++, or maybe a dictionary in Python. It allows you to associate one data type with another. So, for any address, you can map it to a specific integer. Very common to do something like this if you want to track for a bunch of different addresses, which are users of your contract, what their balance is. You might set up a mapping like this. And then for a specific address, you can update that value, you can query it. Very normal thing to do. Now, one note I'll say here, right away we'll come back to this, but message.sender is the address of the person that's calling you, so this function is meant to deposit some money, and it's saying increase the balance of the person who called the function, makes sense, and increase it by message.value is the amount that was actually sent when this function was called. So basically this allows the user to send some money to the contract, and then they'll make a note of it in this balances map that records that that user's balance has just increased. So how is this implemented? It's important to actually dive in under the hood and see how mappings are implemented, because it does have some implications for how you can actually use them. So let's say that we declare a mapping between strings and integers. And let's say that that mapping has 3 values in it. So there's 3 users, and each one of them has a balance. So where are these data values actually going to get stored? What's sort of interesting, very different from how it's implemented in most other languages, rather than trying to put all those values close together to have some locality in memory, they're actually going to get written all over the place to the contract storage. So in particular, if you think about the contract's entire storage, and remember, in Ethereum, any 256-bit address is a word of storage that you can write to. So the way this is actually implemented, the address in memory that Alice's balance gets written to is a hash of the name of the mapping itself and the key Alice. So those 2 values are both hashed, gives you a pseudo-random address in memory, and that's where Alice's balance is actually written. And why is the name of the mapping actually included? Well, that's so that if you have 2 different mappings or multiple mappings in your program that have a key Alice, they won't try to write to the same word in memory. And the same process will happen for anything else that's stored in the map. So notice that these aren't stored in any kind of order. They're going to be all written to a pseudo-random address in storage. And traditionally this would be not a very efficient way to go if you had a normal disk or normal RAM. You'd like to ensure locality. In Ethereum, there's actually no efficiency benefit to storing values close together, so this is the simplest implementation, is to just write them to a pseudo-random address in memory. And maybe you're asking, well, what would happen if 2 different values tried to write to the same address in memory? And of course that would be a collision in the hash function, so as long as our hash function is collision resistant, we can be sure that that's never going to happen. Okay, so I told you that it was important to understand this because it had a few implications for how you could actually use maps. In particular, like everything else in Ethereum, storage is all initialized to 0, so there's no notion of a key not existing in a map. If you query a key that doesn't exist, you'll just get a value of 0. Right, so whatever value you try to look up in the map, it will give you an address in memory. If it's never been written to, it will just be an uninitialized address which has a value of 0, and if 0 has actually been written there, it will be the exact same thing. So there's no difference between a key not existing and a key being mapped to a value of 0. So if you want to tell the difference between those 2 cases, then you'll have to manually write some sentinel value like -1 or maybe int max -1 to represent a value of 0 if you want to tell the difference between those 2 cases. Similarly, there isn't really a notion of deleting a key. Deleting is equivalent to just setting the value to 0. And maybe the biggest functionality limitation, it's not possible to just iterate over all keys which exist in a map. So they can be written to anywhere in memory. Any address in memory can be interpreted for the right key as a value. So there isn't a way, unless you separately store in an array, say, all of the keys that you actually put into that map, to just iterate over all the keys that exist. And an implication of that, of course, is that you can't just delete the entire map since you don't have a list of the keys that exist. So if you care about that, you're going to have to do extra work to keep track of all the keys yourself. So now let's talk about some different ways that your contracts can actually interact with the environment, can read data, and actually have some effects. The most basic thing is to be able to tell who's actually called your contract when it's running. So as I mentioned before, message.sender gives you address of either the account that called you, or maybe you're called by another contract. It will give you that contract's address. And message.value says how much value, how much ether was actually sent along with that contract call. You can transfer value to other addresses. Like I said, anything that's interpreted as an address, you can call .transfer, and that will send some money. And I'll note here that if you just transfer and specify an integer, it will be interpreted as Wei, which is the smallest, the atomic unit of currency in the Ethereum system. If you want to specify it in Ether, there is a keyword Ether, and notice that this is a much, much bigger value. And there's a couple of other keywords for different denominations as well, like Fini and Shabo. And you can also query the balance of any address. So you can, it's all public information, so for any address you have, you can look up how much money that address actually has. This is just one example of something that's deprecated and not meant to be used anymore, but you might see it if you go reading Solidity code. The paradigm or the notation used to be .send to send money. This is unsafe. We'll talk about why in a lecture on security, but just to note that it's changed from .send to .transfer. There are a bunch of other examples of this where the notation has changed. Everything else in this lecture will be up to date, but that's just a note since it's a very common one that you might see that out there. You can also get some information about the current block. So there's a global variable, a special variable called block. You can get the number of the block, which is the index in the blockchain for this specific block. And again, which block is that? It's the block that your transaction is actually executing within. You can also get the timestamp of that block, which is the time that the miner said the block was found. It's not guaranteed to be perfectly accurate, but there are some limitations that will make it close to the current time. You can just do now as an alias for the same thing. And if you want to, you can get some information, some other information about the block, like which miner actually found it. Coinbase is the address of the miner that found the block. How difficult was it to find? You can also query the hash of the block and some other things if you need them. So there's a special function revert that halts execution and rolls back all state changes. Another syntax for that is require, which actually takes a condition and calls revert if that condition is true. That's really just syntactic sugar for saying if this condition, then revert. But it's important to realize that with require or revert, not only is execution halted, but any changes to state that you've attempted to make up to that point will all be undone. So let's say you have a program like this. We have an address of some guy called Andrew, and we transfer a whole bunch of money to that address. But then later on, during execution, the program, say, calls revert. Well, that means that everything's going to get undone, which includes not only any changes to the contract storage, but also that transfer of value to this address here. And any other contract that we've called, if we've called other contracts and they've made arbitrary changes to the state, it's all going to be unwound. So this is a very nice feature for safety. Kind of if anything is going wrong with your program, you can always call revert, which says undo everything that's happened in this specific transaction, this contract call, and go back to the beginning. When your contract is done, when it doesn't need to exist anymore, there's a special function self-destruct, which actually destroys your contract. It takes an address as an argument, and that address is basically your last beneficiary, so any remaining value that the contract has will be sent to that address. Now this is a one-time thing. Your contract can only call it once because it will destroy your contract. And it will halt execution too, so if you have a revert after this, it won't be able to undo a self-destruct. Some contracts never self-destruct, they just stick around forever, but if you know your contract has no reason for existing anymore, you can call self-destruct. Okay, so where things really start to get interesting in Solidity and in Ethereum more generally is when one contract calls another. So the easy case is if you have the Solidity code for the contract that you're trying to call, then you can call it in a very elegant syntax that looks a lot like normal object-oriented programming. So if you want to call this function bar in this contract foo, once you have a foo object here, and notice that for any address you can cast it to be any contract type that you have the code for in your source file. So we can essentially, we're casting this address and saying interpret it as a contract of type foo, and then call the .bar function and pass a value of x. And of course there's a return value here, which will be the return value of this contract. So very, very classic object-oriented programming, which of course requires that you know the Solidity code of the contract that you're calling. You actually don't need to know all of the code. It's okay to just have an interface like this where you don't actually have the function body. The only thing you really need for the compiler to do this for you is the exact signature, so the name of that function and the arguments that it takes. One other thing that you can do when you're calling, if you want to, you can send some value along with your call. So you add this little .value modifier here, and that says not only do I want to call the .bar function in this contract foo, but I want to send it 100 way in this case. Now I said that was the elegant case, which implies there's a not elegant case, kind of an ugly case. If you want to call a function on a contract and you don't actually have the Solidity code for it, then the syntax looks like this. This is called a low-level call. And you have to pass it this function signature, which is a hash of the function name and the parameters that it takes, truncated to 4 bytes. So that's how function signatures are done in Solidity. If you have that, you can call a function kind of dynamically on any address that you want, but it is fairly ugly in your source code. So if you have the Solidity code for the contract available, it's going to make your life a lot easier. Another thing that you can do, you can create a new contract using the new keyword. So much like you create a new object in Java, say. Now, I should note that it makes it very easy to create contracts. Creating contracts is very expensive, so you want to be careful about this, but the Solidity language makes it very easy to create a contract. So note that once this line executes, it will actually create a new foo contract and deploy it on the blockchain, and then you can immediately call some functions on it if you want. And here's where you pass arguments to the constructor. If there was one, I didn't write one out here, but you can see how that would work. So I mentioned earlier that message.sender is a special global variable that gives you the address of the contract or the account that has called you when you're running. There's another special variable called tx.origin, and that gives you the original creator of the transaction that led to this code running. And those can be two different things if you have a chain of contract calls. So let's say that some account A calls a function on contract B, which calls a function on contract C, which then calls you. tx.origin will be account A. That's the account that originally created this transaction. And message.sender is the most recent contract that called you directly. And notice that there isn't currently a way to get introspection about contract B in this scenario or any other contract that might happen to be in the middle there. But important to notice, message.sender and tx.origin, they might be the same thing if you're being directly called from an external account. Otherwise, they might be different. And it's important to use the right one. There are different cases where there are security bugs because people got confused about the difference between these two. So I'll just tell you a couple of other cool features and some best practices. So Solidity does have some built-in functions for accelerating crypto. Specifically, you've got your choice of 3 hash functions, and you've got some basic functions for doing multi-precision arithmetic. So if you want to implement some crypto primitives like RSA or elliptic curve in Solidity, these are going to make your life a lot easier. Another feature in Solidity that's very common, makes your code a lot easier to read, is to use modifiers. So modifiers are usually used as a way to add requirements before a function can execute. So in this first example, this is a modifier that says this function should only be able to be called by a specific address. So note what happens. There's a check to see that message.sender, the caller of this function, is equal to the specified address. And of course, if that isn't true, then that require condition will fail and everything will revert before the function gets a chance to run. So the syntax there is you have requirements, the underscore semicolon says actually run the function body here. If you want, you can have post-condition checks too, although in my experience those aren't quite as common. You can actually combine multiple of these. So I defined a second modifier here, only after, which says this function should only be executed after at a specific block number or greater. And note in this example here, you can combine them. So you have a function that, say, is supposed to end an election. You want to say it's only called by the owner of the election, and it can only be called after the election's end. So this is the most common use of modifiers, rather than having every function, which sometimes you'll see, start with a whole bunch of checks before doing anything, make sure this, and this are all true. You can define them in modifiers, and it gives you kind of a cleaner way to express those. And there's some special modifiers which are built in, which are actually a little more powerful. They have some compiler assistance, which are important to know about. So at the top here, the payable modifier, that says this function can receive funds. So notice that the default for functions is for them not to be payable, which means that if the caller has sent any non-zero value when they call you, it will immediately revert. So any function that's supposed to be able to receive money, you have to manually mark as being payable. View marks a function that's saying that it won't actually modify contract storage at all. And of course, the compiler will enforce that. And pure is even stronger. Pure says that the function won't modify contract storage. It won't even read contract storage. So you might use pure for sort of a library function. And those are just sanity checks that you can have the compiler enforce for you. So I mentioned revert. It's common that you want your program to revert if there's an error rather than just returning, and here's an example to illustrate why that's the case. So this function is called to cast a vote in some sort of election, and notice that it checks two things before allowing the vote to go through. So first it checks that the caller has actually sent enough money, hasn't sent less money than some voting fee. And second, it checks to see if the sender has already voted before. And in the first case, it calls return. In the second case, it calls revert if that's not true. So what's the difference here? Return will halt execution there, but it will commit any changes to permanent storage. Whereas revert, of course, will undo everything. So the upshot of that is that if somebody calls your function incorrectly by passing too low of a fee, the contract will actually retain the fee because you called return instead of revert. Whereas if somebody tries to vote twice, they'll basically get their money back. So you can see why it's considered more polite to revert, because that means you won't be capturing callers' money that they tried to send you if they called you in the wrong way. It's also generally just safer to do a revert, which ensures that no changes are made unless a function actually completes successfully. There's a special function in Solidity called the fallback function, and it's defined with a little bit of a funny syntax. It basically just looks like a function with no name. And the fallback function is what gets called if somebody sends your contract money, or if somebody tries to call a function on your contract that doesn't exist or they don't specify a function. The fallback function is basically the default. So you can have this be whatever you want. Say, if somebody sends you money, you want to record that in some variable. That's fine. You can implement that with a fallback function. The most important thing probably to say is that you usually want your fallback function to be payable, which allows somebody to just send the contract money. So remember, even if somebody just tries to send your contract money, say they use the .transfer syntax, which isn't a function call, it's just a transfer of money, your fallback function will still execute, and if it's not marked payable, it will actually reject that payment. So for your contract to be able to receive money through direct payments, you have to define a fallback function, and you have to mark it as payable. There are a couple of other features, more advanced things that I'm not going to talk about in this lecture that I'd encourage you to dig into. There are some more advanced object-oriented features, so there's a notion of inheritance, interfaces, abstract classes, which work similarly to the way that they work in C++, JavaScript. So I'd encourage you to read up more on the mechanism there. There are some basic facilities for string processing. I didn't cover those in part because they're actually not very commonly used, since you don't define a user interface directly in your Solidity contract. Typically the user interface is handled in some other layer, some other programming language like JavaScript. There isn't actually very much need for reading or writing strings in Solidity. It's not that common, so I decided to skip it. There's a built-in facility for logging, for emitting events, which are recorded in the logs on the blockchain. Also, not too complicated, but I encourage you, if you need that feature, to look it up. There's some more low-level features that you can use. You can actually insert assembly code, EVM opcodes directly into your program if you're sort of an expert and you want some very specific functionality. And I did show you one example, but more generally there's memory and storage keywords that let you control if data is written to memory or to storage. So a couple takeaways. Like I said at the beginning, Solidity and also EVM, the virtual machine that executes Solidity, it was designed for Ethereum, and that's still by far the most common use of it, but it might outgrow Ethereum. So there is the Enterprise Ethereum Alliance, which is looking at applications of Solidity outside the Ethereum blockchain itself. You know, smart contracts are a fairly useful primitive, so there might be other platforms that run them, and Solidity could be a perfectly fine language for developing elsewhere as well. Although maybe you don't think Solidity is a perfectly fine language. If that's the case, I should say that there's no requirement to write in Solidity if you want to develop a smart contract. So you have the option of writing EVM directly. That's the equivalent of writing your own assembly code. It's going to be probably pretty painful for you, but it's certainly possible to do if you need really low-level control. And there's also some competitors to Solidity. So Viper, probably the most popular one, looks more like Python in its syntax than Solidity does. But there are a lot of other people, and I'd encourage you to throw your hat into the ring to develop other smart contract programming languages. As long as you can write a compiler that will take your programming language and produce EVM bytecode, that means that you can deploy your smart contracts on the Ethereum network. And the last thing I'll say is that, like any programming language, the most effective way to learn it is probably not listening to a lecture. The most effective way is probably, of course, writing your own, which you're encouraged to do, and we have some exercises for you to get some experience doing that. Another nice thing about dealing with a blockchain is that you can look at the code for a lot of contracts that are already deployed. So Etherscan is a website that you can use. It actually matches EVM code for contracts on the blockchain with Solidity code that's available on GitHub. So you can look at a lot of different contracts that are actually deployed on the blockchain, and you can examine their code. You can read it to sort of see how things are commonly done in practice. And there's some other nice things that Etherscan gives you. Like you can actually see what the state of different storage variables is in this contract at the current time. You can look at different transactions in which code ran. So there's a lot of tools for you to learn by reading other people's Solidity. And of course, there's the official docs, which I think are actually pretty readable and a good place to start. But you can dig through these if you want to find out about some of the other features that I didn't talk about in this lecture.